Hello. This is a little video about applications of exponential growth, and we're hoping to be able to solve equations like 5 times 6 to the x equals 8,320, and we would probably use natural logs to do that. If I took the natural log of both sides, that would be swell. Bring the 6x up to the front. 6x natural log 5 equals natural log 8,320. Divide both sides by the natural log 5. I'm going to get 6x equals the natural log of 8,320. Oops, I'm supposed to say divided by the natural log of 5. And then x is that divided by 6, and we get some sort of a number. So that's the basic thing. So what's a logarithm? That's a question that we might ask ourselves. What is a logarithm? Remember, a logarithm is this number right here, the 7. See it? Raised to this power is equal to that number. So 7 raised to the x power equals 52. That's what we're trying to figure out. And again, if we want to solve an equation like that, we can use natural logs, natural log of both sides. So I'd get the natural log of 7 to the x equals the natural log of 52. Bring the x out in front. X natural log 7 equals natural log 52. And so x is the natural log of 52 divided by the natural log of 7. Great, doing well now. Oh, then we get a problem like this one. Log base 5 of 3.2 equals the square root of x minus 4. Oh my. So it still means the same thing. It means the square root of x minus 4 is equal to this number raised to this power equals this. So 5 raised to the 3.2 power. Okay, if I now take natural logs of both sides, I should probably, instead of doing this way, as I've probably advised you before, make that to the 1/2 power. Sloppy, but you'll live with it, I guess. If I take natural logs of both sides, I get, and I'm going to do two things at once. I'm going to make it 1/2 the natural log of x minus 4 equals the natural log of 5 to the 3.2, which is just some sort of number we could easily get, right? And then the natural log of x minus 4 is equal to 2 times the natural log of 5 to the 3.2 power. And then to free this up, boy, this is going a ways. I should probably have a number on this. So this is all just a number, so it's okay. To free up the natural log, we use e. So I would do e to this side and e to that side. I'll do like a little dotted e. Frees up the natural log, so I would get x minus 4 equals e to whatever all of this craziness is. And if I had a calculator handy, which I should, I don't see one looking around, but if I had a calculator handy, I could just get this number, and then e to that number gives me a number, and then I add 4 to each side, and I get an answer for that particular problem. And we've gone back through and we figured it out. We just got to make sure that the number that we end up with isn't like some number smaller than 4, which it shouldn't be because of 4 plus something. So we should be okay on that one, just to check to make sure that it all turns out to be legal. All right, so what's exponential growth? Things grow in two ways. They grow linear, which is just by adding a constant rate, or they grow at a rate that is proportional to itself. So the rate of growth is proportional to the current, I'm going to say population. So whether we're talking about people or germs or money in a bank or any other thing, so the rate of growth is proportional to the current amount, the current population. So whatever you have, the rate of growth somehow depends on how much you have. So if you have more of something, it grows faster. E is the limit, the n gets really, really large, of 1 plus 1 over n to the n power. That's what E is. Yeah, if you do that on the calculator, you take a minute, you do 1 plus 1 over 1,000 to the 1,000th power, 1 plus 1 over a million to the millionth power, whatever the limit of your calculator comes out to be. It's going to get very, very close to E. And that's how E is defined, and E numerically is 2.71828, and then it keeps going on and on and on. It doesn't keep repeating the 1828. So E is another one of the famous irrational numbers. Compound growth. This is the way that money grows in a bank. Okay, this is the amount of money that you have at a certain time. It's called the principal. It's what you have in the bank, and it's this kind of principal, not the other kind of principal. This R is your interest rate. How much money the bank is willing to give you in time, and it's as a percent. So usually some sort of a decimal equivalent. So like 8% would be 0.08. N is the number of compoundings, which just means how often does the bank give you interest. If they give it to you once a year, then N is 1. If they give it to you 12 times a year, then N is 12. Okay? And T is time in years. Okay? So this is an annual interest rate. So it's an annual interest rate. We divide by the number of compoundings. That breaks it down to quarterly or weekly or monthly or something like that. And A is the amount that you have after time. Amount after T years. And so we can use this, and we will, to figure out how much money you make in interest, if you put something in the bank for 10 years at this rate, depending on the interest rate. Now, as opposed to compound growth, there's this thing called continuous growth. And with continuous growth, what happens is that N becomes infinite. Okay? N becomes, they're just constantly giving you interest. Not once a day, not once a second, continuously. So there's no real time length. So essentially, N goes to infinity. And so with N going to infinity, we start to look like this thing starts to look like the equation we had before, or at least we get the 1 plus 1 over N to the NT. And so it turns into compound growth, A equals P e to the RT. Okay, and P is just principal like it was last time. R still my interest rate is a decimal. T is still time, but E is E. And you've got an E button on your calculator, by the way. So what I would have you do, if you want to, and I think you should just to practice it out, is if we have money in the bank for 5 years, you would start with $1,000, get 5% interest. How much money are you going to make if you compound it quarterly, which means that N equals 4, or weekly, which means that N equals 52, or continuously, which means you use this formula. So for the first one, we would say A equals 1,000 times 1 plus, what do we make it, 5% interest, which is crazy, over quarterly 4 times, to the N, which is 4 times 5 years. So turn the handle on that with your calculator, see what you get. Then do the same thing with 52 weeks. Then jump over here to this equation and see how much better you are if you get interest compounded continuously, which means non-stop. The interest rate is 0.05. The time is 5. Just as a comparison. Okay, and it may not be a lot, compared to $1,000, but if you got $1 million, or well, if you had $1 million, then good for you. So, what's A primed? What does it tell you? And what does the integral of A prime tell you? So A primed is the derivative, right? And by now we should know that the derivative. Let's try that again. By now you should know that the derivative of e to the u is e to the u, du. So A primed is going to be P times e to the RT times the derivative of RT, which is R. Okay, so A primed is R times P e to the RT. Okay. So basically what that's telling you is it's exponential growth, and exponential growth, the rate of change, is proportional to the amount that we have. This is the amount that we have, the PERT part. Okay, this is how it's changed. This is the interest rate. So that's the constant of proportionality. Okay, so what's it tell you is it tells you how fast your money's growing. It gives you that indication of, the rate of change of your money over time. What's the integral of A prime to tell you? So the integral of a derivative. Okay, the integral of the rate of change. If we integrate a rate of change, we get the total change. So if we have money in the bank and we know it's compounded, getting interest compounded continuously, we can figure out how much money we get into the bank, how much our value, how much we've changed by from this point to that point. Okay. There's this thing called logistic growth, and it's the way rumors spread, the way illnesses spread, the way diseases spread. Rumor basically spreads, and this is not the best picture of it, but it's it starts out a little flatter, and then it kind of goes like this, and then it kind of levels off. So, if there's a rumor going around, a couple people hear it, and then suddenly it hits this crescendo where everybody's talking about whatever it is, and then it gets to the point where everybody's heard it and it levels off. Or sometimes if there's a sickness, a disease, flu or something going around, a few people get it, few people get it, few people get it, and then suddenly it just spreads like wildfire, and then eventually it levels off because because everybody has the thing, or most people have the disease, have it, and there's no one else to give it to, so it levels off. And that's called logistic growth. And so we might want to know, like, how is this thing changing when t is equal to 4? And so the rate of change is the derivative. And I would probably, let's see, how would I take the derivative here? I might rewrite this as 1.25 times 1 plus 0.25 e to the negative, 0.4t to the negative 1. Might be easier to deal with. And so y primed is going to be negative 1.25, because I'm just going to multiply by negative 1, times 1 plus 0.25 e to the negative 0.4 t to the negative 2, multiplied again by the derivative of this whole part in here. Derivative of 1 has gone away. The derivative of 0.25 e to the negative 0.4 t is, well, 0.25 e to the negative 0.4 t multiplied by the derivative of negative 0.4 t, which is negative 0.4. And at this point, if we wanted to know what the rate of change was, how fast was whatever this thing is spreading, how fast it's spreading, we'd plug in t equals 4, and we'd get ourselves some sort of number that would give us an indication. Is the rate of change? Is it up here, or are we getting towards more flatlined relatively, or are we in the peak portions of things? So you can calculate that as well if you like. Okay, and then the limit as t approaches infinity, as t gets really, 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 really big. What's going on here? So, well, as t gets really, really big, 1.25 is 1.25. 1 is 1. This part, as t gets really, really big, this part gets really, really negatively big, right? And so we have e to a really negative power, right? And if we remember the shape of the e thing, e to the x power, e to the x, it gets really, 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 really close to 0. So this part gets really, 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 really close to, this gets really close to the 0. E to the 0 is 1. 0.25 times 1 is 0.25. 1 plus 0.25 is 1 plus, so it levels off at 1. Okay, which would indicate, that 100% of the people have the thing as time goes on. Okay, so there's that. Logistic growth, just an application. All right, so there's that. Hope those are the problems that you should be working on. I don't know if I can get back where I want it to be. I just keep going forward, and I don't know what to do about that. So, did I go back? For some reason, it doesn't let me go back anymore. It kind of makes me sad. Oh, there it is. Okay. So, applications of E. Thanks for watching. Hope you learned something, and we will be talking to you soon. That's all for now.